Good afternoon and welcome. Today I'm going to be doing Resistivity 2. I'm going to do a walkthrough through that and explain how some of the questions, because I know some of you had some difficulty with this. Okay, so resistivity is really important because resistivity is a material property of conductors and insulators too. So for example, water has a resistivity of 1 times 10 to the 10 ohm meters, which means for a meter's worth of water, there is going to be at least 10 mega ohms worth of resistance. So it can still conduct. It's just ridiculously resistive, which means that's going to take a lot of potential away. So if you try and conduct electricity through water, the water itself is going to take a lot of the potential away because of V equals IR. Now, on the flip side, copper has a resistivity of 1.7 times 10 to the minus 8 ohm meters, which means that per meter, there's going to be about 17 nano ohms worth of resistance, which means that not much potential is going to be lost, which makes it a much better conductor. And this is where this whole idea of everything technically is a conductor, but it's all depending on how much it resists. So when we go, it's not really a conductor anymore, it's actually more of an insulator. So it uses that electrical potential as heat to itself. Okay, so we're talking about electrical conductors and electrical insulators. This is very different from thermal conductors and thermal insulators. So we're going to talk about here is we're going to talk about, first of all, I'm going to remind you about potential dividers, and then we've got some questions here about resistivity. Okay, so let's start with potential. So this is a potential divider because it's an object which here splits up the potential. So you've got R1 and R2, and that splits up the potential. And what we're asking here is what happens to the actual thing when this V out. So if I stuck a voltmeter here, what would happen in certain situations? So this is saying if R2 goes down. So if R2 decreases, V equals IR. If R goes down, its potential goes down. So what happens is this one, the potential will go down. And what happens to V out if R1 decreases? So this one is going down. So this is going to lose potential. Because of Kirchhoff's law, they've still got the same amount of volts going in. If this is losing potential, this will be gaining it, which means that this is going to be higher. Okay. So in this question here, this is another potential divider, but instead of using 2 resistors, I'm actually just using a thermistor and a resistor. So this is a temperature-controlled resistor. So what it's asking me here is at 25 degrees, this one is 36 kiloohms, and at 25 degrees, this has a resistance of 24 kiloohms. And it goes, what is the voltage measured between A and B? So what it's asking is if there was a voltmeter here, what would that be? So this is a series circuit. And so what I'm literally going to do is I'm actually going to work out some information and actually work out some things. So with most of the thermistors, you could use the potential divider formula for you. So you could use V of the resistor that you're after is the total thing times by the resistor here over the sum of the resistors. So the resistor that you're after there. You could do that if you wish, but I'm not going to do it that way. I'm actually going to do it the way that I would do it, which is a bit longer, but it's, for me, feels a little bit more comfortable. So my total resistance is going to be 36 plus 24, which is going to be 60 kiloohms. So I missed out the kilo, but I knew they were the same unit. My total voltage is going to be 12. So using V equals IR, I know that I is going to be 12 divided by 60 times 10 to the 3. Oops. 10 to the 3, which is going to be quite small, 2 times 10 to the minus 4. Okay, so that's my actual current there. Now I know the current going through this. So I know the current going through this is 2 times 10 to the minus 4 amps. I can work out the actual potential over this using V equals IR. So I've got V equals 2 times 10 to the minus 4 times by 24 times 10 to the 3. And that's going to be 24 times 10 to the 3. Oops, not 33. It's going to be 4.8 volts there. Okay. If you wanted to know the voltage on the 36 kiloohm resistor, I could use Kirchhoff's current voltage law and know that 12 is going to equal the voltage on the 36 plus 4.8, because you get a nice loop going around like that. That's my loop. Okay, so I've got V of the 36 is going to be 12 minus 4.8, which is going to be 7.2 volts. So as you can see here, the 36 is getting a little bit more voltage than the 24, and that's because it's got a bigger resistance. But it's not considerably more. It's not like a 50-50. It's not like it's double the amount. It's just a little bit more because it is slightly bigger. So if the thermistor increases, the temperature drops. And that's just a reminder that thermistors, as the temperature gets bigger, the resistance gets smaller. And that's all to do with the charge carriers, that it releases some more charge carriers, which means that there's more current in the circuit, which means that the resistance of the circuit must have gone down, and that was caused by the thermistor. So I'm going to do exactly the same as I did before. So I'm going to go, my total resistance is going to be 36 plus 4, which is going to be 40 kiloohms. Okay, so my voltage is going to still be going to be 12. It's the same battery. I times by 40 times 10 to the 3. So I is going to be, so 12 divided by 40 times 10 to the 3. So the current is going to be much bigger this time. It's going to be 3 times 10 to the minus 4. But my resistance on this thermistor is much, much lower. So that on the thermistor is going to be 3 times 10 to the minus 4 times by 4 times 10 to the 3. So times by 4 times 10 to the 3, and it's going to equal 1.2 volts. So as the actual resistance goes down, so does its voltage. Okay, so that's just a recap on potential dividers. Hopefully that will recap your memories. What we're going to do now is I'm actually going on to resistivity. So this one here is a wire, has a resistance of R, when the resistance is both the length and the radius of the wire are doubled. So this is one of those questions that's asking you to manipulate a formula. So I know that rho, the resistivity, is RA over L. The reason I know to use rho was because all of a sudden, after resistance, it's talking about the length and the radius, which means that it must be something to do with something that changes with when I change the actual size of the object, like mass would do. So that's how I kind of had an indication that something was happening here. Okay. Now, it's a wire, and so R is actually going to be pi, delete all of that, sorry about that. R, my area is actually going to be pi R squared, okay, over L. So if I actually now rearrange this, so I've got rho L over pi R squared equals R. So I now know, I want to know what happens if I double the length of the wire and I double the resistance. So what happens if I do that? I've got rho 2L over pi 2R squared, which is going to be 2 rho L over 4 pi R squared. Sorry, trying to find some space for this. So things will start cancelling, okay? So just going to change the colour of this. So what happens, this 2, and that will change to a 2. So I've ended up with rho L over 2 pi R squared. And this section here is R. Okay, so now I'm ended up with R divided by 2, which is B here. Okay, so that's kind of normally how I do them. I will write down what the equation normally is, and then I start manipulating it. And I go, cool, that section there, there's R, because you can see it equals there, and I will make that there. So the answer is B. Oh, we got to love this one. So this one, the two resistors are shown with uniform cylinders of equal length and are made from the same conducting putty. So they have both got the same resistivity. So the resistivity of this is exactly the same as the resistivity of this. Okay. The diameter of Y is twice that of X. The resistance of Y is R. What is the resistance of the total combination? Oh, that's a bit mean. So let's actually have a look at this here. So I know Y has a resistance of R. Okay. The diameter of Y is 2 times the diameter of X. All right. So if these were the same size and same things, you would add them together, and that would be 2R. Okay. So I'm actually trying to work out the resistivity of this one here. So how I'm going to do this, I'm going to work out the resistivity of Y. Okay. So resistivity is R A over L, which is going to be R pi R squared over L. So R equals pi R, there you go, rho L over pi R squared. Okay. So this is of course for the length of Y and the radius of Y there. Okay. So I apologise, my cat is going scatty. Okay. So I know that the diameter of Y is twice the diameter of X. Okay. Which means that I know the radius of Y is twice the radius of X. So the radius of X is RY over 2. And the length is exactly the same. This is where they're being really mean. Okay. So what's going to happen here is we're going to bung this into the formula. So we've got the R of X is going to be rho L of Y. Okay. And of course it's going to be pi, and technically it would be Rx. But I know Rx is Ry over 2 squared. So now I'm going to manipulate the formula a little bit more. So this would end up as rho Ly over pi Ry squared over 4, which of course would then be 4 rho Ly over pi Ry squared. And magically, that section there, sorry about that, this section here, is R. So I know that the resistance of X is going to be 4R, because it's 4 times R. So this one's R, this is 4R. They're in series with each other, add them together, and you end up with 5R there. So it's quite a mean question, and sometimes will take a little bit more than 1 minute to do. So here, Ohm's law. Ohm's law states that the resistance or voltage is directly proportional to current under constant temperatures. So this is one of those questions that they love asking, because what they do here is they like the part where the temperature remains constant. So looking at them asking the current through the conductor between 2 points is directly proportional to the potential difference across those 2 points. So the voltage is directly proportional to current under a constant temperature. So that would give you your 1 mark. It may be a 2 mark question because I'm asked. So I did jump the first part. This is a very standard question, define Ohm's law. So this is a cylinder of putty, which is 60 millimeters long and 20 millimeters in diameter. They say that a 1.5 volt DC supply of negligible internal resistance, and again, that negligible internal resistance, now you've done it, you may actually understand what that means. It has there's no other resistance, is connected to the end. So if I'm just going to put that there, I've got a lovely resistor like that, and that's what it looks like. The resistance of the putty is 20 ohms, calculate in milliamps the current in the putty. So this is literally what the circuit looks like at the top. There's no other things here. So I've got my total resistance is 20. My voltage total is 1.5. So it's going to be I times by 20. So I equals 1.5 divided by 20, which is going to be, 0.75 or 75. This is where it's important, the units here. Okay, 75 milliamps. Okay, I did see some students write 0.0075. Please make a check of those units, and that there itself is worth 1 mark. Okay, the students suggest this arrangement. Ooh, that's horrible. But they instead suggest this arrangement for demonstrating Ohm's law. Discuss any problems that you make with the circuit. Now, this was actually done quite poorly, and this is because it's a practical question that you're not probably used to. And it's all to do with, so a student suggests this arrangement. Discuss any purposes, any problems Let's just do it with my pen. I was doing it with my mouse and it didn't work. So discuss any problems that make it unsuitable for its actual purpose. So there's a couple of things. So some people did get the right idea that the voltmeter is incorrect because you're measuring, you want to find that the putty obeys Ohm's law. I'm just going to put this down into a separate sheet so you can actually see the whole question. So a lot of people were correct, and well done for realising that to measure putty's voltage, voltmeter must be across the putty, not the cell. Okay, so that's the first thing, and I did see that done well. A lot of people really noticed that, so well done for that one. Okay, that was actually worth 2 marks. So you're actually realising that it must be across the putty and not the cell. But it's the second mark that a lot of people fell down with, and this is actually a practical question here. And it's all to do with, if you're trying to find that it follows Ohm's law, you actually need a very broad spectrum of results for the current. And this is one of the biggest problems, is that this here is 20 ohms maximum. Okay, so the maximum resistance is going to be 30 ohms. And the minimum resistance is going to be 10 ohms, which means that the maximum current you're going to read is going to be 0.15 amps. And the minimum current you're going to read is going to be 1.5 divided by 30, so 0.05. There is not much room for you to actually get an experiment out of that at all, because there is so little difference between the maximum and the minimum. So you're not going to get enough data. And this is actually where the second mark came into it, and students didn't kind of pick that up. And it's because you're not used to practical questions yet. So basically, the 10 ohm resistor does not provide enough results to see if Ohm's law is obeyed, because it's the amount of results you're going to get is, let's say you're able to get it up by 0.1 amp each time, it's going to be really, really, really small. Okay, so what you could have then done here is so the question is, discuss any problems that will make it unsuitable for those purposes. It's actually not talking about how to change it. Okay, so the 10 ohm resistor does not provide enough results. This is because the current ranges from 0.5 to 1.5 amps, which isn't enough. And that itself is actually worth the mark, that the examiner can see that you can realise that there's a problem with the amount of results we're going to take. And again, that is a practical kind of question. So if they ever ask you, what's the problem with this thing? Look at how many results you can get. What's the minimum value you could have got, and what's the maximum value you could have got? And have a look at that. But a lot of people got the first bit, so 2. The second bit was a bit hit and miss. This one, sorry about the editing. It should be this. Oh, Christ. On this one. So rho equals R over L squared times by V. And it's just proving that is for a wire. So the volume of a wire, so really cheeky, they're using different blinking letters, is the cross-sectional area times by L. So if we were to put this into the formula, so rho equals RA times L over L squared, you'd get that L cancelling with that, getting RA over L, which is correct. And that was just worth 1 mark. It was quite a simple question, but they like doing it. Sorry for the formatting, it would be much better in an exam. Okay. So using the formula, so using rho equals R V over L squared, give an appropriate unit for your answer. So this is still going to be, resistivity is still going to be in ohm meters, and that's worth 1 mark. You can just get away with just writing that. So what we're going to do here is we know that the diameter is 20 millimeters. So the radius is 10 millimeters. So the area is going to be pi r squared. So 10 times 10 to the minus 3. Remember to convert squared times by pi is going to be 3.14 times 10 to the minus 4. Okay. So the volume is going to be 3.14 times 10 to the minus 4 times by 60 times 10 to the minus 3. 1.88 times 10 to the minus 5. Okay, and then of course using the formula, so 20 times by 1.88 times 10 to the minus 5 all over 60 times 10 to the minus 3 squared times by 20 divided by 60 times 10 to the minus 3 divided by 60 times 10 to the minus 3. I get an answer of 0.11. Okay. Just want to double check that because I feel I've done something a little bit wrong on that one. I do apologise. Yeah, 0.11. Okay, so it's 0.10. Okay, so there's not a rounding thing in here. There's not standard. There's not to the appropriate number of significant figures. It gives an appropriate unit. So for this question here, you get 1 mark for your method and 1 mark for the answer. Please, please, please make sure that something I didn't do was actually put the blinking thing in the blinking box. All right. If there's an answer line, put the answer in the answer line, or the exam board will not be happy with you. Okay. So, oh, this is good. The picture went missing. The wire probe is used to measure the rate of corrosion in a pipe found in a corrosive liquid. The probe is made from the same metal as the pipe. Figure 1 shows the probe. The rate of corrosion of the wire is the same as the pipe. Okay, so what I tell you here is information about the pipe. So the pipe has a resistance of 0.07. Its length is 0.5 meters. Calculate the diameter. So that's something to do with finding the area. And the resistivity is 9.7 times 10 to the minus 8. So rho equals RA over L. So the area equals rho L over R. So that's going to be 9.7 times 10 to the minus 8 times by 0.5 all over 0.07. So that's going to give me the area. So 9.7 times 7 times 10 to the minus 8 times by 0.5. Oops, can't actually do any maths today. Times 10 to the minus 8 times by 0.5 divided by 0.07. So then my area is going to be 6.93 times 10 to the minus 7 meters squared. And that's going to be pi r squared. So I'm going to find the radius. So divide that by pi and square root it. My radius is 4.69 times 10 to the minus 4. So my diameter is going to always be twice my radius here. So that's 9.4 times 10 to the minus 4. Okay, so this is actually worth 3 marks, 1 for actually getting the answer, 1 for your method, and 1 for the rearranging here. So there's a method and the actual rearranging and getting the value for R here. Okay, so that's these ones. They love asking for this. They love asking for diameter, or they like giving you the answer in the diameter. Okay, in order to measure the resistance of a working probe, it is connected in the circuit shown. Oh, love editing. So the pictures, that is the picture for figure 1. I will now move it to figure 1. Sorry, that's annoying, isn't it? Wait there. Ta-da! Okay, that's just bad editing, sorry. So in order to do this is actually a circuit diagram here. This is where the probe is put. It's put into a circuit like this, and R3 is adjusted. So this is a variable resistor. So the current in this cell is 0.66. So this is 0.66 amps. Okay, you calculate the total resistance of this circuit. Okay, so you know the total voltage is 1.5 volts. You know the total current, can't actually do the letter for the current today, is 0.66. So you end up with 1.5 equals 0.66 R. So your total resistance is going to be 1.5 divided by 0.66, which is going to be 2.27 or 2.3. Now, this is actually really important. When reading this question, I know a few students are overwhelmed with the amount of information. So this is the thing I do. I've got a lovely diagram here, and they give me when R is adjusted. So okay, R is a variable resistor. That makes sense. Particularly to the current in the cell. This word here, this means the current or the total current in circuit, and this is because it's the current that is going through the cell. If you know the total current voltage, which you do, and you now know the total current, you can use Ohm's law, V equals IR. It's one of the most powerful things you can do, and this is probably what I'm going to be doing for the whole of the circuit. Okay, so this brings us on to how I do the next one here. The resistance of R2 is 22 ohms, and the resistance of R3 is 1.2 ohms. Calculate the current in R3. So if you actually draw on the circuit, and you can draw on circuits all you want, this is exactly what I'm doing here. I know that if an electron was to be going round, it will go from here, and it could go this route round here and come back. Or of course, it could go a slightly different route, so a different colour, go through, oh, blinking Nora, go up here, go through here, and go through this section of the actual circuit. It could go either one. Okay, this is the orange route. Okay, so remember Kirchhoff's law. Kirchhoff said that if you're going around in one loop, the potential that you are given is the potential you must lose in total. So I know in total across this whole branch, this whole track must have lost 1.5 volts. And luckily for us is these two resistors are going to have the same amount of current going through them. It's not the total current, but I know that they're going to have the same amount of current because as you can see, the current comes in and it doesn't split up. So I know that in total, the potential across this section here is going to be 1.5. And the resistance total for that section, A for B, is going to be 22 plus 1.2, so that's going to be 23.2. So V equals IR, so 1.5 is I times 23.2. Your current is going to be, so 1.5 divided by 23.2, it's going to be 0.0647. So 0.0647 amps. So it's very, very low, okay? And what I then do, because this is how I learned how to do electricity, is I write that on my circuit. I will literally go 0.0647 amps. I will write it on there because now I know how much current is going through here. So this section here is going to have 0.66 minus the 0.0647, which is going to be 0.66 minus that, which is going to be 0.595. Okay, so this here is going to be 0.595 amps, and now I know that, and I can use that later on. So I'm embellishing my circuit as I go around. So it says here, calculate the resistance of the probe when the resistance R1 is 2.4. So this is 2.4. And again, this is going to be the purple route. So the electrons are going to be losing that here. So this is the purple route here. Woo. So the electrons are going to be losing 1.5 volts as they go through R1 and the probe. And I know the current going through it now, which is really, really useful because, again, it's just me annotating my diagram. And it's really, really helpful. So I know the current in the circuit is 0.595. So 0.595 amps. And I know the voltage total is going to be 1.5 volts because if you go around the purple route, that is the only time they can lose that voltage. So V equals IR, you can actually work out the total resistance of that section. So I've got 1.5 equals 0.595 times by R, so that's going to be 1.5 divided by my answer, 2.51 ohms. So that's my total. And that's going to be R1 plus R of the probe equals 2.51. So I know that that is R1. So I've got 2.4 plus R of the probe is 2.51. The probe is going to be minus 2.4. It's going to be 0.12. Okay, so that's actually a really different way of approaching it. So I've seen very many different approaches. What I did is I knew that was the current and that's worth a mark. I knew I could work out the total resistance, and from that, I could work out that. Another way you could have done it is with the current and the voltage, the resistance. You could work out the voltage across that. So another method, so I'm just going to do this in the corner in a different color. So you could have done the V of 1 is going to be 0.595 times by 2.4. So that's going to be 0.595 times by 2.4, 1.428. So 1.5 minus 1.428 equals 0.072. So this is how many volts is across the probe. And of course, that's the probe there. So you can go 0.72 equals 0.595 times by the resistance of the probe. And you get an answer of 0.12 again. So that's an alternative method and completely valid. Okay. But as you can see here, I'm just drawing all over my circuit. That's fine. Just draw all over the circuit. It makes it really easier. Calculate the percentage change in the diameter when the resistance is increased by 1.6. So the probe resistivity is R A over L. Okay. If the diameter is increased by 1.016, the resistance is increased by 0.16. Okay, so 16%. Okay, so what we're going to do here is bring it all into the formula. So I've got R is rho, and that's going to stay the same, times by pi 1.016 R squared over L. So 1.016 squared, oh Christ, 1.03. Okay, so I've got rho R equals 1.03 rho A over L. okay, or if I should change that again, pi r squared over L. So the change here, I've got 1.03 of r, because that there is r. Whoops. This, of course, is the new r of the old. So it's a 3% change because it's 1.03, which is approximately about a 3% change. But check the mark scheme. Did I read the question wrong? Did I read the question on? Oh, I'm looking at the change of diameter. I thought diameter was changing. Ignore that. I'm literally just going to rub that out. I was doing if the resistance the diameter increased, not finding what the diameter was. That's me being an absolute pillock. Start again. Same method though. So the resistance is going to be, the new resistance is going to be 1.016 of the old resistance. Okay. So let's rearrange this. I've got the area equals RO L over R. There we go. Cool. Sorry about that. It's me being an absolute wazzock. So that's my traditional area. So my new area. So this is my area here. So I know that pi r squared equals rho L over R, and that's the old one. The new one is going to be pi r new squared equals rho L over the new R, which is 1.016 R. Okay. So I've got 1 over, I've got pi r squared equals rho L. Oops. So 1 over 1.016 rho L over 0. So this is the new one. R. This is the new one here. So what I've got here is 1 over 1.016. So that's 0.98. So pi r squared equals 0.98 rho L. So this is a new of basically pi r squared there. And loads of things cancel out. So pi cancels out. So just to make you aware, that is that there. So this is the old area, okay? Or to be more specific, looking at the formula that I've got up here. So I know that I'm going to square root it to get it out. So I know that the new radius is going to be 0.9, answer, square root my answer, 0.99% of R here. So this is the new radius is going to be 0.99 of the old radius there. So the change in the radius is going to be 0.01, which is about 1% there. Okay, so that was a bit long-winded. I do apologise. I made a mistake to start with, which just put me a bit on the back foot. But what I've done is I took the equation for the resistivity. I knew that the resistance had changed by 1.016, and this is representing a change of 1.6% numerically. Okay, so I know the area can be rearranged as area equals rho L over A. So I know that traditionally pi r squared is rho L over R. Okay, I know the new radius is going to be pi r new equals rho L over 0.016 R. And of course, I know that this section here, this rho L over R, is actually my old radius. So I'm inputting that information and I ended up with this formula here. Okay, so this is the formula I'm ending up with, which is actually probably one of the most important formulas that we're using here. The method, just to go through, I end up with Rn squared equals 0.98 R squared. square root the lot, I end up with Rn. The new radius is 0.99. So the change in my radius, and this is the important thing, that's what they're looking for, the percentage change is going to be a change of about 1%, which is the mark here. So there's a method mark and the mark percent here. It's actually quite a big question. I read it wrong to start with. It can happen. I was like, why is it only 1%? I'm getting about 10. Okay, so just to make you aware here. So question F, a voltmeter is connected to these points here. So what a voltmeter is doing when it's there is it's measuring what voltage is coming in from this one and what voltage is going to come in from this one. And so in this case, let's actually work it out quickly, just so I can show you what it would read. In this situation, 22 times 0.0647, this is going to, 22 times 0.0647, this is going to have, so the voltage across this one is 1.42 volts. And the voltage across the top one, so 2.4 times by 0.595, 2.4 times 0.595 is 1.42. So as you can see here, there's no difference between them. So this potential difference, the difference between this point and this point of the voltage that's remaining left. So as you can see here, I've got 1.5 going in, and I'm going to have 0.8 across each of these. When the put a voltmeter there, it looks at how much is left at point A, how much is left at point B, and it will find the difference between them. In this case, the difference is none. There is no difference between them. And this question is asking, a voltmeter is connected to A and B, and R3 stays at 1.2 ohms. Explain, without calculation, why the reading of the voltmeter does not change when the cell of the circuit is replaced with that but significant internal resistance. So what it's explaining, so this is, you might understand a little bit more about this now, is that if there was another resistor here, everything about this section, it stays exactly the same, but I'm going to put another little resistor in the circuit. So what it would look like is this. So the circuit would look like this. So it will have your cell, it will have an internal resistor here, and that's your cell there. It will come up, you would have your resistor there, your wire, your resistor here, and then it will come back round again. So what actually happens, now you understand, is that this little internal resistor will remove some of the potential and it will change the current of the circuit. But explain without calculation why the reading of the voltmeter, so explain why this will still read 0. And it's all to do with the fact that you are not changing anything about how the percentage of the split of current. You think about it, both these probes are still going to have the exact same voltage across them. Whatever's left after the internal resistor has taken it away, it will still have exactly the same across in each branch, which means that it will have the same difference between them. So the actual Mark scheme's answer, if you go through, is the correct reference to lost volts will terminate or reduce current, reference to resistors not changing, reference to the voltmeter having infinite resistance, reference to be very small, closeness of the resist ratios, etc. like that. So what is actually, the way I would have answered this, so it's a 2-mark question, so 2 points, and it goes, since the resistors are not changing in the branches, the split of current is the same. So whatever current is left will still be split up in the same ratio. And because it's V equals IR, the same ratio split would mean that you have exactly the same potential. Okay, so since the resistor are not changing in the branches, the split of the current is the same in terms of ratio, in terms of fractions. Okay, so it's split up the same with this. This means the PD between the points will be the same, even though the values at A and B will be smaller. So I know that the value, the actual numbers these are going to have, so currently these have got 1.42 volts each. I know that number is going to be much, much smaller, but I still know that the difference between them, because they're still going to have the same fraction ratio of current. So let's say this was 1 volt and that was 1 amp and that was 2 amps. I know, so that's a 1 to 2. I know if the current changes and I've only got 0.3 amps coming in, I know that's going to get 0.1 and that's going to get 0.2. So I know the voltage is going down, but I know they're both going to go down at the same rate. Okay, so if I look at the mark scheme for this, corrections to lost volts is going to reduce current. So I said that in same branches, the PD across the value will still be the same. Reference to resistors not changing, which is the first thing I said. And references to PD being very small due to the closest to the radio, which is what I proved there, or which is what I've said here. So I've said the PD between the same, even if the values would be smaller. So I've mentioned about the current affecting it here. And I've mentioned about the fact that the resistors are staying the same there. Okay. So last question here. So we've got question 5. Figure 1 shows the circuit in thermistor T with a variable resistor. So it's a potential divider, but this time with 2 variable resistors. Here we go. This is the experimental potential divider. It's a circuit of 2 or more resistors in series that splits potential between them. And that's it. It's the regurgitating stance. You should know what a potential divider is and how to do this. So the exam board say a combination of resistors in series connected to a voltage source. So to produce it require pretty reference to splitting, not dividing. So you must mention splitting. It doesn't divide the potential, it splits the potential. So it explains what happens to the voltmeter reading when R is increased while the temperature is remained the same. So 3 marks. So if the temperature is constant, the thermistor resistance is the same. That's me just writing out for you. That's a quick one before we go back to that circuit. The temperature is constant. This means that the thermistor will have the same resistance. So it's a state and explain jobby, as per usual. You've got to say something and what will happen. So I'm just explaining a little bit first that the temperature is constant, the resistance is constant. So what's actually happening is this thermistor, this one here, is going to stay the same, and this one is going to increase. Kirchhoff's laws as per usual. So if I just grab a different colour, if I just grab a colour here, going around here, I know that the voltage on the resistor plus the voltage on the thermistor equals the total voltage. Okay, so I know if one of them is staying the same, the resistor is going to go up. So here, and so it's reading on the voltmeter. This is quite important. So the voltmeter is across the thermistor. Okay, and so if the voltage across R is going to go up, this means the voltage across T is going to go down. So temperature constant all through, so the resistance is constant. This means since the total equals the thermistor plus the R, and the voltage of R is increasing, this means the voltage over the thermistor, which equals the voltmeter, would decrease. Okay, so if I look at the mark scheme here, it says when R increases, the potential across R increases, mentioning that the voltmeters across the supply, and mentioning the maths involved in actually stating it. So I get 1 mark for stating it, which is this one here, which is the decrease. Okay, so that it would decrease. Whoops. Going back. So you get 1 mark for saying the actual voltmeter would decrease, and then you get another 2 marks for explaining. So I'm mentioning the fact that the thermistor is constant, and actually mentioning that the sum and the maths there. So state what explains to the ammeter reading when the temperature of the thermistor increases. So this is important. So again, 2 marks. So ammeter reading. Okay, so this is important. The ammeter measures the current. So when temperature increases, the resistance decreases in thermistor. Therefore, the total resistance decreases. And since V equals IR, if R is decreasing, I increases. So what I'm saying here is that the current will increase because the fact that I'm mentioning what happens to a thermistor at that point there. Okay, so we just go to the mark scheme. At a high temperature is lower, the resistor is higher, so the current increases. Exactly what I just said. The current, the ammeter reading is increasing. So the battery has an EMF of 12, and so I'm going to draw my circuit again. So I've got this one here. So this is 12 volts. The resistance is 2.5 kiloohms on the thermistor. And R here, the voltmeter is replaced by an alarm. So it's got an alarm here. So I'm just going to do a speaker. That sounds when it's got 3 volts across it. Calculate the resistance of R that would cause the alarm sound. So I want 3 volts across this. Basically, I want to have 3 volts. So if I want 3 volts across this, there's going to be 6 volts across that. Okay. So you can actually work out the current going through the circuit because you know the resistance. You know the resistance at this section, and you know the voltage you have. So I've got 3 equals I times by 2.5 times 10 to the 3. Okay. So 3 times 2.5 times 10 to the 3, or divided by, sorry, I do apologise, is going to be 1.2 milliamps. And now, because of Kirchhoff's law, I knew that was 6 volts because 12, 3, 2. I know that 6 equals I times R, so that 6 equals 1.2 times 10 to the minus 3 times by R. So R is going to be 6 divided by that, which is going to be 5,000. Just want to double check something. Or was I double checking? I actually can't add up. I do apologise. It's not 6, it's 9, isn't it? I was like, I knew the answer was 7,500, and I'm like going, it doesn't make sense. And that's because I can't apply Kirchhoff's laws correctly. So that's 9 volts. So that should be 9, and that should be 9 there. So 9 divided by that, and that's going to be 7,500 ohms there. So that was my fault. I can't do Kirchhoff's law. 1 mark for the method, 1 mark for that there. State 1 change that you would make to the circuit so the alarm is coming on when the temperature falls. So this is what's happening here, is that a temperature is of 0 volts as 2.5 times 10 to the 3. As it gets hotter, that resistance is going to go down, which means that this voltage is going to go down, which means the buzzer is going to turn off. So state 1 change you would make to the circuit. So instead of the alarm coming on when the temperature falls, it comes on when it gets hotter. So what happens when it gets hotter, this thermistor is going to lose voltage, while this resistor is going to gain voltage. So what you want to do is you want to flip them over. So you want to put the resistor, put the alarm over R, not T, because as temp increases, the resistance of R, or the voltage of R, will also increase. Okay, and that's just because of how a thermistor works. So that there was a couple of questions on a mixture of resistivity and potential dividers, and they can be used in conjunction. But as you might have noticed as I was going through, I was consistently using Ohm's law, or I was consistently using Kirchhoff's law. Very few times did I actually go, I'm going to use a snazzy formula. No, I didn't. I literally just worked out things bit by bit, and you are more than welcome. Draw all over your circuits. That's absolutely fine. Doodle like I am. You're more than welcome to. You're not going to be penalised for doing that. Okay? So what I'm going to do is I'm going to upload this video onto Google Classroom, and then I'm also going to do the next one, which is internal resistance. So hope this helps, and take care.